So we've now talked in detail about the chemistry of water, and the next topic to tackle in our look at water is the hydrologic cycle, also known as the water cycle. So the hydrologic cycle describes patterns of movement that water follows between different states and reservoirs on Earth. This includes the liquid water that's found in Earth's oceans, lakes, rivers, and aquifers, the solid water that's found in glaciers and ice caps, and finally the gaseous water vapor that's found in the atmosphere. And water is continuously cycling through these different states. And so we're going to walk through the hydrologic cycle and see how those transitions happen. And our starting point to the hydrologic cycle is going to be liquid water. So liquid water is found in many forms on the surface of the earth, and it's also found in the surface layers of soil. When that liquid water transitions to a gaseous stage of water vapor, this is known as evaporation. So, evaporation takes place from the surface of oceans, lakes, and rivers, but it also occurs out of the top layer of soil. And this evaporation is where the water vapor in the atmosphere comes from. There's also one other source of atmospheric water vapor, and that is plants. So plants contain pores in their leaves called stomata that are used to draw in carbon dioxide gas and spit out oxygen gas. And you can see a microscope image of one of these pores here. And these stomata not only exchange gases that are involved in photosynthesis, but also serve as a portal through which water evaporates out of the plant. And this process of water evaporating out of the pores in plant leaves is called transpiration. Then there's also a term that we use to describe the combined vaporization of water from transpiration out of plants as well as the evaporation of water out of soil. And that term is evapotranspiration. So evapotranspiration includes evaporation from sources that include plants and soil, but not evaporation from the Earth's bodies of water. So bottom line, there are several pathways by which liquid water gets turned into the water vapor that we find in the atmosphere. But once it's there, the water vapor gets carried upward as it rises with the rest of the air. And as it rises higher in the atmosphere, it cools. And the cooling of the water vapor causes it to undergo condensation, which is the process of a gas turning back into a liquid. And as a result of condensation, droplets of water form in the atmosphere. And as those droplets accumulate, they will combine with others to form larger droplets until they become visible in the form of clouds. Eventually, when the droplets become large enough, they can no longer remain aloft in the atmosphere, and gravity pulls them back down to Earth's surface. And this phenomenon is called precipitation, the process of water falling from the clouds as rain, snow, sleet, or hail. So now that the water has returned to the surface of the Earth, what happens to it next? Well, some of that precipitation will flow deep into the ground. This process of deep water absorption is called infiltration. Water that infiltrates deep enough can become part of what we call groundwater, underground bodies of water, also known as aquifers. Aquifers are what people tap into when they dig a well to source their water. And the upper surface of the aquifer is called the water table. So to be able to access groundwater, you have to dig deep enough to reach the water table. And before we carry on with our journey through the water cycle, we need to take a moment and talk about the importance of aquifers, because aquifers represent a significant source of fresh water that is used for human consumption. About 30% of the liquid fresh water on Earth is stored in underground aquifers, and humans draw heavily from them for their water needs. However, aquifers are not as renewable of a source of water as one might think. Aquifers are filled through precipitation that falls over a space of land known as their recharge area. And only a fraction of that precipitation infiltrates down into the aquifer. So as a result, it can take hundreds to thousands of years for an aquifer to fill, especially in areas that receive little precipitation. To give you some perspective, aquifers in the Sonoran Desert, for example, our region, contain water that soaked in thousands of years ago. And now, a multi-decade long drought in the Southwest that has caused even lower precipitation rates that are hurting aquifer recharge. On top of that, humans are drawing out the groundwater at a rate that is much faster than it's being replenished. And it's so fast that water experts in Arizona consider much of that water to be quote unquote unrecoverable or unlikely to ever be replenished. A common way that the volume of water in an aquifer is measured is by looking at well digging data to assess how much the water table has dropped. So, in other words, how deep does the well have to be dug in order to access the water table? And many wells in Arizona have existed for decades. So we know that groundwater levels are dropping as people have to go deeper and deeper to access the water table. And this figure here shows the number of feet that the water table has dropped in various regions of the state of Arizona since the year 1950. So you can see the scale on the left ranges from 0 feet dropped all the way up to over 160 feet. And at the high range, that's about the height of a 16-story building. So water levels in 1 in every 4 wells in Arizona, 25% of wells have dropped by more than 100 feet since they were drilled, and nearly half of all wells in Arizona have dropped by more than 50 feet. And the most severe drops are taking place in rural areas where there are no laws regulating how much can be pumped out of the ground. So, for example, the agricultural basin around the city of Maricopa in Pinal County, the water table there has dropped 125 feet since the 1950s. So, needless to say, we are overdrawing our aquifers, and that is a serious threat to water resources in our state. And we'll talk more about water resources in the state of Arizona later, but for now, let's get back to the water cycle. Okay, so we know that some precipitation water infiltrates into the ground and becomes part of groundwater stores, but eventually soils may become saturated with water and no more water can infiltrate. So at this point, overland flow will take place. Overland flow is known as surface runoff. It's the movement of precipitation water over the surface of the ground. And it gets carried to streams, rivers, or other mobile or stationary bodies of water. And once it's part of a river system, the movement of the water from there is referred to as stream flow. And eventually, stream flow carries the water back to the ocean. We refer to the geographic area that is drained by the stream flow of a particular river as a drainage basin. And for perspective, this illustration here shows the drainage basin of the Colorado River, which covers the path of the Green River as far north as Wyoming, which meets with the Colorado and Utah, and then travels south into Arizona, down along the border of Arizona and California, and eventually drains into the ocean in the Gulf of California between the states of Baja California and Sonora down in Mexico. A few final details we need to talk about in the hydrologic cycle are groundwater discharge and glaciers. So, groundwater doesn't just get extracted from aquifers by humans, it can also seep upward through a spring. And this process is known as groundwater discharge, also known as seepage. And then finally, we can't close out the water cycle without addressing solid water as well. Glaciers and ice caps are actually the largest reservoir of fresh water on Earth. About 69% of the planet's fresh water is found in the form of ice. They're just not commonly used as a direct water source because they tend to be remote, far away from human settlement, and of course they're solid, not liquid. But the huge amounts of water that they store means that changes in glaciers and ice caps that occur as a result of climate shifts can have some significant consequences for the state of water on Earth. During the last ice age, up to 50% more water was stored in the form of glaciers than it is today. And because more water was tied up as ice and less as liquid, at that time, the sea level was about 100 meters or about 300 feet lower than it is today. And in addition, a jump in sea level rise has been observed over the past century as Earth warms and ice caps and glaciers melt further. This figure right here shows the increase in sea level since the year 1880 based on two separate measurements that track very closely with each other, tide levels and satellite measurements. And as you can see, sea level has risen nearly 10 inches since the year 1880, and it's on track to rise further as global climates continue to warm. Now, in our next section, we're going to be talking about human water usage. But before we do, we need to lay down some basic information about the availability of fresh water on Earth and some terminology referring to the different types of fresh water sources and the methods of water use. So, out of all the water on Earth, 97% is saline, meaning salt water, and only 3% is fresh water. And saline water is useless for most human enterprises because of its high salt content. And so, when we're looking at water as a resource for human consumption, we're really only looking at the 3% that is fresh. Of that 3%, as we said, about 69% is found in ice caps and glaciers. About 30% of it is stored in underground aquifers, and that leaves about 1% to exist as liquid in a surface source like a river or a lake. And of that 1% of liquid surface fresh water, about 87% is stored in lakes, 11% is found in swamps, and 2% is found in rivers. So, overall, the message here is that fresh water is a rare and precious resource, and it's one that humans rely on for many, many things. Um, Before we talk about the different sectors of human water use, though, let's establish the different categories of usable water. When we talk about usable water, there's 4 different categories that water managers have created into which all the fresh water can be divided. Blue water is the term used to describe fresh water that comes from sources like rivers, lakes, and aquifers. Blue water is the most readily available and easy to access, but because of this, it is also the most stressed source of water because it's being overdrawn. Green water is rainwater that's stored in the soil and used by plants for growth. It's used to sustain ecosystems and agriculture, although here in Arizona, our agriculture really isn't sustained by green water, it's sustained by irrigation with blue water. Gray water is wastewater. It comes from domestic sources that are not contaminated with fecal matter. So, this can include water that comes from doing your dishes, doing your laundry, bathing, etc. Gray water can be readily used for landscaping and irrigation of non food crops, but in order for it to be used for human consumption, it of course has to be treated. And then finally, there is black water. Black water is wastewater that comes from toilets, so it is heavily contaminated with urine and feces. And this water is considered a biohazard and it has to be heavily treated before it can cycle back into use for any purpose, including for agriculture. So, those are the 4 categories of usable water. And just to give you really quickly some idea of how our state's water resources are distributed across those categories, this chart does not include green water, which remember is rainwater, which in many parts of the state is a very small amount. But among the other categories of usable water, 36% of our water is sourced from the Colorado River, brought down from the northern parts of the state in canals. 18% is sourced from in state rivers like the Salt River and the Verde River, and 41% is groundwater that comes from aquifers. So all 3 of these are blue water sources. The remaining 5% is reclaimed water. So this is the gray and black water sources combined and labeled reclaimed water. So as you can see, in Arizona, the overwhelming majority of water is blue water, the most strained and stressed category of usable water. Now that we understand the different categories of usable water, let's look at the different sectors that use water. There are 6 main sectors, the first of which is the industrial sector. So this sector uses water in manufacturing processes. The agricultural sector uses water for growing crops. The domestic sector uses water for household purposes, which can include landscaping. The livestock sector uses fresh water to supply to livestock, and also uses it for aquaculture or fish farm operations. The mining sector uses water to mine ores or coal or other fossil fuels. And then finally, the thermoelectric power sector uses water in the generation of electricity. How much water is used by each of these sectors varies widely from place to place. But again, to give you an idea of how the pie is sliced in our state, here's a figure showing the breakdown of Arizona's freshwater withdrawals by sector. Now, this does not include green, gray, or black water. This only looks at how the blue water is being used. But remember, the blue water is the overwhelming majority of the type of water that's being used for human activities in Arizona. So as you can see, almost 76% of blue water goes to agriculture. A little over 20% goes to domestic and municipal use, and then the other sectors consume very small amounts. These four sectors together add up to about 4%. In our next section, we're going to be looking at water consumption patterns in the country as a whole and how they're distributed across these sectors. But just a few more terms to define before we get there. Human water use can be either consumptive or non-consumptive. Non-consumptive use is when water is removed from a source, but then returned right back to that source after it has served its purpose. So an example of non-consumptive use could be the use of water to cool a nuclear reactor. The photo that you see here is of 3 Mile Island, which is the notorious nuclear generating station that underwent a partial meltdown and almost caused catastrophe in 1979. It's now been decommissioned, but it's called 3 Mile Island because it's located on an island in the middle of the Susquehanna River in Pennsylvania. And in terms of water use, the middle of a river is a great place for a nuclear power plant because nuclear power plants use a lot of water for cooling nuclear reactors. So they can withdraw that water from the river, use the water for cooling, and then route that water right back into the river, and that's considered non-consumptive use. Consumptive use, on the other hand, is when water is removed from a source and then it's not returned, it's fully used up. So an example of consumptive use is withdrawing water to supply to livestock. The livestock drink the water, it becomes part of their bodies, part of their physiology, and it doesn't get put back into the aquifer or the lake or the river from which it was withdrawn. Another term used in the realm of water consumption is withdrawal. Withdrawal is the total amount of water removed from sources, including both consumptive and non-consumptive use. And then finally, return flow is the amount of water that gets removed from a source but later returned. So essentially, it's the water that's dedicated to non-consumptive use. So keep these terms in mind because, as I mentioned, in our next section, we're going to be getting into more detail about what water usage looks like in our country.